All right, welcome to this video. In this video, we'll be looking at real numbers. We'll look at different types of real numbers. We'll look at ways of writing or notation to write those numbers. We'll look at properties of the real numbers. And then finally, we'll look at something called the absolute value of real numbers. All right, when you look at real numbers, we've separated them into lots of different names. These circles, when you look at the circles, it might look confusing to begin with, but everything within a circle is part of that number system. So these numbers off to the side there, I'll move those into where they should belong. A natural number is a counting number that doesn't include zero. So a number like 5 would be a natural number. Now, being a natural number also, because it's in the blue circle, means that 5 is also a whole number. It's also an integer, a rational, a real number, and a complex number. But at the base, it would be a natural number. Now, numbers that include 0, or a number system that includes 0, is called the whole numbers. So they include all the natural numbers plus 0. Whole numbers sort of interesting that they include a 0 and that's it. But again, whole numbers, 0 would be classified as an integer, a rational number, a real number, and a complex number. Okay, integers, typically people think of integers as being negative numbers, and that's indeed what gets added to the number system. But negative 4, I guess 0 would also be classified as an integer. But negative 4 is also a rational number. It's also a real number, also a complex number. But at its base, it would be an integer. Rational numbers are all numbers that have fractions in them or decimals. I shouldn't say all decimals. They're all decimals that are non-repeating, that they sort of stop. So here's a fraction, that's easy, that's a rational number. But a number like negative 2.15, it's a decimal, and there's no indication that that repeats or doesn't repeat. So I would assume that it repeats forever. There'd be a 0 at the end of that, and a 0 would repeat forever. So that would be an example of a rational number. It's also a real number, also a complex number. It's not an integer because integers are only those counting numbers that also include negative numbers. Okay, so negative 2.15, it's a decimal. It falls as a rational number, which is also a real and a complex. Okay, irrational numbers are, according to those decimals, they're ones decimal places that don't repeat. And it's sort of hard to identify those. Like negative 2.15, I would say that that's a repeating decimal because I could put a 0 at the end forever. There's certain numbers, though, that when you try and figure them out, it turns out that they never repeat. Their decimals never repeat. Like you may have on a calculator done something like 1 divided by 3, and that comes out to 0.3333, and it just keeps repeating forever. When you take the square root of a number, if it doesn't come out even, like the square root of 9 comes out to 3, so that would be classified as a whole number. Anyway, a square root of 27 doesn't come out evenly, and so that decimal never repeats. And so an irrational number is a number that never repeats. So root 27 would be classified as an irrational. It's also a real number, also a complex number. Okay, imaginary numbers are numbers that, and we'll get into these a little bit later, but they are numbers that take the square root of a negative number. So if you take the square root of, say, negative 5, another way of writing that is instead of having a negative, I'll try that on your calculator. Go to square root of negative 5, it'll give you an error. But another way of rewriting that is the square root of 5, and then instead of having that negative there, we put an I. We'll talk about complex numbers and imaginary numbers later. Anyway, this letter I indicates that you have an imaginary number. So if I have 7i, that's classified as an imaginary number. Also, I can say it's a complex number. When you include a complex or an imaginary number and a real number, we call that a complex number. Oh, here's an example of one. Square root of negative 27, it's a square root of a negative number, so it falls into the imaginary number category. All right, so that's sort of a quick description of the number systems within real and complex numbers. Now, when we're referring to groups of numbers, there's different ways that we can do that. Rather than listing them all, there's shortcuts to do that. And we have basically three ways of showing that. One is set builder notation, another is interval notation, and the last is a number line. So for example, if I say, how much money do you have to take in order to pay for $1 hot chocolate at Tim's or wherever? So you can say, well, you have to take $1. Well, you really have to take $1.05, right? Because of tax. And so I could take $1.05, or I could take $2, or I could take 5 or 10, or etc. So there's not just one answer to that question. You could take a ton. But rather than listing them all, you could do something like this. In set builder notation, we would say something like this. So my answer are all the answers, all the x values, as long as x is greater than or equal to whatever it costs for the hot chocolate. We'll say $1.05. Okay, so in set builder notation, to answer that question, I'd say, as long as you took at least $1.05, you could pay for your hot chocolate. You could take $1 million, $1 billion, be a little overkill, but that would answer that question. Now in interval notation, we do the same similar kind of thing, but it's a little easier than this one. In interval notation, all we do is we have two brackets. They could be curl brackets, or they could be square brackets on both sides. You just pick one of them, and then you show the smallest number that you can here, and you show the largest number in the next slot, and you put a comma between them. Okay, so in this case, the smallest amount of money I could take to pay for that hot chocolate would be $1.05. And I can include $1.05, and so I put a square bracket there. If I couldn't include it, I'd put a curly one. Comma, then the largest number, well, there probably isn't one. I could take as much money as I wanted. So I'd probably, in this case, put an infinity sign there. An infinity sign always has a curly bracket on it. Now, those are two of the ways. Another way that you could write this is with a number line. So if I have a number line, and here, say I have 0, here I have 1, 105 would be in here somewhere. I could say anywhere from here on, that would be a solution to that equation. So there's three ways that you can write a group of numbers. So why don't you try it with these three? I've given three examples there of ways of writing set notation, interval notation, and number line. And you just need to fill in the blanks. So why don't you hit pause and try and fill those out, and then hit play, and I'll answer it for you. Okay, interval notation for this one. It's equal to there, so my smallest number would be -4, and there's a square bracket. My biggest number can get up to 1, but it can't include 1 because there's no equal sign there, so I put a curly bracket there. For the number line, I'd say from -4 all the way to a +1, curly bracket there. That would be my range. Interval notation, number line are really related to each other. So similar to this one, I could write my number line, √3, here's 0, √3 is over here somewhere. So anywhere from √3 and up, that would be a way of doing it in the number line. Set notation, I only have one sort of anchor point, and then the other's infinity. So I would write it something like this. All the x's, as long as x is greater than, and because of this, I put an equal sign, √3. Last one, I have a number line. It looks like everything is less than 4. So I'd say all my x's as long as x is less than, can it be equal to? No, because that's a curly one. So x is less than 4. Now to do this one in interval notation, my smallest number, like it goes on forever this way, so my smallest number would be infinity. But the largest number I can get up to looks to be about 4. Can I include 4? No, because it's a curly one, so I just leave a curly one there. Right, hopefully that clarifies those three notations. All right, now when we're dealing with real numbers, there's different properties that we can use. And I'll refer to these lots when we're solving equations or simplifying expressions. There's lots of these. The commutative property for addition and multiplication, not division or subtraction, means that it doesn't matter what order you add two things. So for example, if I have A plus B, that's going to be the same thing as B plus A. Or 2 plus 3 is going to be the same thing as 3 plus 2. In multiplication, AB is equal to BA. So it's a commutative property. Associative property is when you've got three things, three or more, where you're doing things with them. So for example, if I'm adding A plus B plus C, I could say, well, let's add these two first. And you can do that, or if you wanted to, add the B and the C first and then add A. That's legal too. That's the associative property. Under multiplication, it would look like this. If I have A times B and then C, that's the same thing as A times B times C. Or if I put in numbers, say 2 times 3 times 4 is the same thing as 2 times 3 times 4. Let's just confirm that. 2 times 3 is 6, times 4 is 24. Here, 3 times 4 is 12, 12 times 2, 24. Yeah, rule works. The additive identity property means that if you add 0 to something, it doesn't change it. So A plus 0 is still just going to be A. The additive inverse property says that if you add the inverse of the first thing, so if you have an A and then you add the inverse of that, or you change the sign of that, then that's equal to 0. Okay, here's three more properties. Multiplicative identity property, so if I'm multiplying something, and if I multiply it by 1, it doesn't change what I'm multiplying. We use that property all the time when we're solving equations, and we probably don't think about it, but I'll identify it when we get to there. Multiplicative inverse property is if I multiply A by its inverse of A, then my answer comes out to 1. The distributive property means that if I have any term and I'm multiplying it by a binomial, or two things that I'm adding together, I can use the distributive property and I multiply the A by the B first and then the A by the C. So this would be AB plus AC. We could do a practice of that. If I say had this, according to this distributive property, it means I have to go 2 times 3 plus 2 times 4. Well, let's see what we get on this side. 3 plus 4 is 7, and 7 times 2 is 14 I get on this side. Let's see if we get that on this side. 2 times 3 is 6, 2 times 4 is 8. Sure enough, 6 plus 8 is 14. So that's a distributive property. Why don't you try it and just see if you can identify which of these properties is which. I've put a bunch of things over there. It's sort of a matching game. If you want to just sort of pause for a second and see if you can match all of those mentally, and then you press play and I'll do them for you. Okay, so this one here looks to be the distributive property to me. This one, multiplicative identity property, right there. This one, it doesn't matter the order, that's a commutative property. This one, multiplicative inverse property, because you're multiplying by the inverse. This one looks to be the commutative property again, but this one is over multiplication. Oh no, it's not commutative, it's the associative, but it's multiplication, not addition. Where's the addition one? Here's the addition one right there. So it doesn't matter what order you group things if you have three of them, and that's over addition or multiplication. Here's the commutative one for addition. This one, additive identity property, so it must mean this one is that one. Okay, good. Hopefully you have those. All right, last section or concept for this video is on absolute value. And absolute value just means how far are you away from zero. A lot of people indicate, and they just say, well, absolute value, all you do is you lose the negative sign. And that's, if you're doing a question, that's basically what that means. But by definition, it says how far are you from zero. So say if I have the absolute value of 7, here's 7 right there. How far am I away from 0? I'm 7 units away. Notice that the answer to this one, absolute value of -7, here's -7 over there. The distance from there to 0 is also 7, just 7. So there's no direction or anything. I'm just saying how far are you from 0? I'm 7 away. So over here, if I say, what's the absolute value of -123.5? Well, how far from 0 are you? You're 123.5 units. Doesn't matter if you have fractions, decimals, or whatever. In this case here, what's the absolute value of -5/7? It would just be positive 5/7. Okay, why don't we try a couple questions there with that. So this question here, what they're asking us to do is to figure out how far it is between two numbers. And so if I have -5, they say, what's the distance between -5? Here's -5, here's +5. They want to know what the distance is between them. Well, you can just sort of take a look at that and say the distance is 10. But if you had some other numbers there, it might be a bit more difficult. And so a nice little formula that you can use is this right here. So the distance between any points of any real numbers is the absolute value of A take away B. So let's try that with these two numbers here. So the absolute value of, we'll call this one A, minus B is 5. Notice I put brackets in whenever I replace variables, just so I don't mess up on negative signs. Okay, so this is the same as -5 minus 5. You're down 5, you lose another 5, you're down 10. But then the absolute value of -10, I just want to know distance. I don't care about how far or what direction, so that would just be 10. And that's what we sort of thought of to begin with. Why don't you try these ones here? So what's the distance between -4 and 11? Maybe you can see right off the bat that that's 15. Let me do it here on Desmos. Desmos is sort of a nice little tool that you can use to do these. So I want to take the absolute value. So there's an absolute value sign in the bottom left there of, I'm going to do my brackets, -4, bracket, take away, that's my formula, take away, bracket, 11, bracket, done. Okay, and there it gives me my answer is 5. Oh, maybe I need another bracket. Oh, I just put a 1 there instead of an 11. That's why I'm wondering, how am I getting 15 out of it? There's 15. Okay, so the answer to this is 15. You can do the same thing with the next one. Let's try that one. Okay, so -2/5. Okay, absolute value of -2 divide 5. Nice that it puts in brackets there. Then there's some arrows there underneath the word function that you can use to move over a bit. So -2/5 minus 8/15. 8 divide 15. 15. There we go. All right, so my answer to this one comes out to be 0.93 repeating. Now, a little awkward with decimals. I haven't figured out how to change that to a fraction. It'd be nice to have that as a fraction. But you could do the common denominator thing here and just use that formula, A minus B, like I was trying to do in decimals. And when you use your common denominator, you'll come up with something where you divide it and you're going to come up with that same answer. Okay, so in this video, we have taken a look at what real numbers are. We looked at natural numbers, whole numbers, rational numbers, irrational numbers, real numbers. I think there's a different term for or symbol for rational numbers, and complex numbers. And we've looked at properties of those numbers, and we've also looked at the absolute value of real numbers. Okay, so now go ahead and try some practice questions, and we'll talk to you in the next video.